Hello, welcome again. We are covering the topic centrifugal compressor for civil services main IFS and Gate Aerospace. And in this, we are covering the subtopic design of compressor through some examples. And in the first example, we have solved A part. Now, in this video, we will solve B part. So, B part is to calculate the inlet angle of impeller vanes at the root and tip radii of the eye, assuming that the axial inlet velocity is constant across the eye annulus. So here this is your eye, okay. And we have taken in this diagram we have taken a section at radius r1 and drawn a velocity diagram. So here it is given that the axial velocity is constant, so axial velocity is perpendicular to the paper or along the axis of the shaft. As shaft is here, it is rotating it, so it is in this direction. So it is in this section, I section, and in axial direction. So with the velocity of ca1. So absolute velocity, there is no worm component. So this is the absolute velocity also. So c1 is equal to ca1, and it is constant throughout this section. Here it is ca1, here it is ca1, here it is ca1, here it is ca1. Okay. But this u is different at I root and at IT, because u depends upon radius. So here radius is different, here radius is different. So this will be different, but this will remain same throughout. So this can be calculated for both I root and I tip, because root diameter is given, tip diameter is given, I root diameter is given, tip diameter is given, and speed is given. Okay. So the speed can be calculated, this u can be calculated, but we need this also. It is given that it is constant throughout, but its value is not given. So if we use continuity equation, and because mass flow rate is given, that is 9 kg per second, if we use continuity equation, so we need density also to calculate this. Okay. So if we use this continuity equation, m dot is equal to rho 1 a1 ca1. So we don't have ca1, we don't have rho 1. Okay. So we don't have density, we don't have axial velocity. So there are two unknown here. So we cannot calculate by simple method the axial velocity. Okay. We cannot calculate the axial velocity by simple method. So we have to follow an iterative procedure, because here stagnation pressure is given, stagnation temperature is given. From the stagnation pressure and first step in the iteration is, from the stagnation pressure and stagnation temperature, we will calculate density. Okay. And after calculating density, we will find out the ca1 from the mass flow rate. This may be wrong, because rho 1 will be very high, because we have calculated from stagnation condition, and ca1 may be very low. Okay. But what we will do, we will calculate from this ca1 that we have calculated from here, we will calculate static temperature and static pressure. Okay. And after calculating static pressure and static temperature, we will find new density. Okay. And then we'll find out new ca1 and check whether it matches the previous one or not. Okay. So if it matches, then it is okay, otherwise we'll take the new axial velocity and follow the procedure. So here the procedure is like that. So area, first of all we need area. Endless area is here, the flow is entering actually, okay, flow is entering in this circle, in this angular portion. So the area of this angular portion is pi d tip square minus d root square by 4. So that is your 0.053 meter square. Okay. So that is your area of impeller. Okay. So now from stagnation condition, T01 is known, T01 is known, we will find out density. Density is at 1.3 kilogram per meter cube. And now from continuity equation, using this density we will calculate axial velocity, that is 131 meter per second. Okay. From this, because this CA1 is equal to C1, there is no bulk component, so from this we will calculate dynamic temperature, that is your C1 square by 2. Now if we subtract this dynamic temperature from this stagnation temperature, then we are able to calculate static temperature. So that will come out as 286.5. So now using isentropic condition, we will calculate stagnation pressure, because P01 is known, T01 is known, T1 is now known. So P1 will come out as 0.992 bar. Okay. So now we will calculate new density based on this T1 and P1. So that will come out as Rho1, that is your 1.21 kilogram per meter cube. Okay. So now we'll again use this continuity equation and find out axial velocity. So it will come out as 140 meter per second. So there is huge gap between this 131 and 149 meter per second. So now we will use this again, find out dynamic temperature, and then new static temperature, and then new static pressure, then new density, and then new axial velocity, until the compromise is made between them. So here we are taking the final trial. So we have reached, so skipping the trials in between. So we have taken CA1 as 145 and check whether it satisfies our condition or not. So CA1 is 145, from this dynamic temperature is 10.5, and T1 will come out as 284.5, okay. And P1 will come out as 0.968 bar, and Rho1 will come out as 1.185 kilogram per meter cube, and then CA1 will come out as 140. So there is no much difference between 140 and 145. So we can take this as your velocity. Okay. So after finding out velocity, we can find out the angles from the diagram. So this is the diagram. If we take a tip velocity, that is your 273 meter per second, pi into 0.3 into 290, then it will be this angle, tip angle, and if we take this 136.5, then it will be root angle. Okay. So I will read the iterative procedure so that you can note down. To find the inlet angle of the vanes, it is necessary to determine the inlet velocity, which is this case is axial. CA1 is equal to C1. CA1 must satisfy the continuity equation m dot is equal to rho 1 A1 CA1, where A1 is the flow area at inlet. Since the density depends on C1, both are unknown, a trial and error process is required. The iterative procedure is not critically dependent on the initial value assumed for the axial velocity, but clearly it is desirable to have some rational basis for obtaining an estimated value of starting the iteration. The simplest way of obtaining a reasonable estimate of axial velocity to calculate the density on the basis of known stagnation temperature and pressure. In practice, there will be a density that is too high and velocity that is too low. Having obtained an initial estimate of the axial velocity, the density can be recalculated, and then the actual velocity from the continuity equation. If the assumed and calculated velocities do not agree, it is necessary to wait until agreement is reached. Only the final trial is shown below. Note that it is normal to design an axial velocity of about 150 meter per second. This providing a suitable compromise between high flow rate unit frontal area and low flexibility. And this I have explained. So this is the procedure, iterative procedure, and the answer is this 46.2 27.67.